Hey everybody, this is Peter from peterstestprep.com. Today we're going to talk about probability. This is part one of probability. This is the stuff that everybody should know for the ACT exam math section. As with all of the videos, there's a link at the bottom of the video in the description. A worksheet is what you will click on, and you will print that worksheet out, and you should follow along with the video. Wherever I suggest that you stop the video and do the problems, please do so. And that is the best way to learn this material. You will keep this worksheet and you will study it and you will know it when you take the ACT exam. And as you do that with all of our videos, it'll maximize your chances to getting the best possible score. And so with that introduction, let us begin. All right, well, let's start with page one. I'm going to zoom in here and we're going to be in the left-hand column. And we're going to start off by talking about probability of multiple events happening. So let's see what your feel is like for doing these types of problems. Why don't you stop the video and take a look at 1A and 1B. Looking at 1A, the probability that the Giants will win Monday is 0.4, and the probability that they will win Tuesday is 0.5. The probability that the Giants will win both Monday and Tuesday will be, well, let's think about this. You have a certain probability of winning today. You have a certain probability of winning tomorrow. Do you think it'll be easier or harder to win both games? Well, of course, it's going to be harder to win both games. And so the probability has to be less than 0.4. It has to be less than the probability, the smallest probability of winning any one game. In 1B, we have the same situation, but this time the question is what the probability will be that the Giants will win Monday or Tuesday. So again, we ask ourselves, you have a certain probability of winning today and a certain probability of winning tomorrow. Will they have an easier time winning just one of those games, either one? And of course, it should be a higher probability, so it'll be greater than the greatest probability, 0.5. All right, so let's go on to our first substantive lesson. This is section 2, finding the probability of multiple events occurring. To find the probability of multiple events, each occurring, determine the probability of each event occurring individually, and then multiply those numbers. These are sometimes called AND problems. We're asked, what is the probability, I'll just abbreviate that, of this happening and that happening? What is the probability of this happening and that happening? Let's take a look at a simple example. 2A, Edna will roll a fair die and flip a coin. What is the probability that she will roll a 6 and that the coin will land on heads? Well, let's take a look at the die first. There's a 1 out of 6 chance, of course, that it will land on a 6. And then we'll look at the coin, and there's a 1/2 or 50% chance that it will land on heads. And we're just going to multiply those numbers. And the probability of both of these things happening is 1/12, a number that is much smaller than these two individual probabilities, and that's exactly what we would expect. Let's talk about terminology real quickly here with die. I always was uncomfortable with that word. One die, well, you don't say one dice, you say one die. Two or more die, well, that's dice actually. So one die, two dice, or three dice, however many it is. A fair die is a die that has an equal probability of landing on each side. What if you have a die that does not have the same opportunity of landing on each side? Well, are we going to call that an unfair die? I don't know. Maybe a weighted die usually, right? A weighted, it's got an imbalance of the weights inside of it. All right, with that understanding, stop the video and let's have you try the problems 2B, 2C, and 2D in the section immediately below. These problems in section 2 are about as straightforward as they get for multiple events. For 2B, the probability of rain on Saturday is 1/3. The probability of rain on Sunday is 2/5. Find the probability that it will rain on both days. So the probability of Saturday is 1/3. The probability of Sunday is 2/5. And we're just going to multiply those numbers, and we get 2/15. In 2C, the same situation as in 2B, the same probabilities for Saturday and Sunday. What is the probability that it will not rain on either day? Well, the total of all the probabilities of something happening always has to add up to 1. So if there's a 1/3 chance of it raining on Saturday, then there'll be a 2/3 chance of it not raining on Saturday. If the probability of rain on Sunday is 2/5, then the probability of not having rain on Sunday is 3/5, and we're going to multiply those numbers, and we're going to get 6/15, or that can be reduced to 2/5. Finally, in 2D, a couple has 3 boys and 1 girl. Every night a child is selected at random to do the dishes. What is the probability that a boy will be selected 3 nights in a row to do the dishes? Well, for each of the 3 nights, the probability is exactly the same. 3 out of 4, since there's 4 children. We're just going to multiply 3/4 times 3/4 times 3/4. First night, second night, third night, and the total probability is 27 out of 64. These are called independent events, and that's what we're going to talk about next. These are all independent events in which the probability of what happens the first time has no effect on the probability of the second and third events. So let's go to page 2, and we will look at section 3 on the top left. We have the classic bag that contains 4 red marbles, the 4 R's, and 2 blue marbles. Ebenezer will select 2 marbles, one after another, from the bag. Now there's 2 situations to look at. First, 3A. In the first trial, Ebenezer will select a marble, record its color, and then return the marble to the bag. This is called with replacement. Then he will select a second marble. What is the probability that both marbles will be red? Well, for the first selection, the probability is going to be 4 out of 6 because there's 6 marbles, of which 4 are red. Now, because he puts the marble back in, whichever marble he selected the first time, it does not affect the probability of selecting a red marble the second time. So with the second choice, the probability of selecting a red marble is still 4/6. What's the probability of selecting both red marbles? 4/6 times 4/6, and that's equal to 1636, which we can reduce to be 4/9. By the way, if you do not know how to use your calculator to reduce a fraction, and there's a really, really easy way to do this, make sure you stay tuned at the end of this video, and we will quickly cover that. So, calculator to reduce fractions at the end of the video. Make sure you stay tuned. Now, getting back to our problem, because the selection of whichever marble we select the first time has no effect at all on what color the marble is going to be or the probability of selecting a red marble the second time, we're going to call these independent events. So independent events, the result of the first selection has no effect on the probability of the second selection, and the key phrase is usually going to be with replacement. You are putting it back in, you are replacing the marble. Let's look at 3B now. Same thing, Ebenezer selecting 2 marbles. In the second trial, Ebenezer will select a marble, record its color, then place that marble on the ground. He is not going to put the marble back into the bag. This is called without replacement. Then he selects a second marble. What is the probability again that both marbles will be red? Well, the first time it's 4 out of 6. But we're going to assume that he selects a red marble, but he does not put it back into the bag. Well, this reduces the number of marbles in the bag, and it reduces the number of red marbles. So now there are only 5 marbles left. 3 of them are red. So in this second case, the probability of selecting a red marble is only 3 out of 5. We've eliminated one of the red marbles. We multiply those numbers, and we get 12 over 30, or again, reducing that, we get 2/5. So these are dependent events. The probability of the second selection depends on the result of the first selection. These are called dependent events. All right, let's go to the right-hand column here now. I'm going to have you do a couple of problems here. In both cases, identify, are you looking at an independent or dependent collection of events? and then find the probability. Solve the problem, so do 3C and 3D. Stop the video. In 3C, Alice has 5 chocolate chip cookies, 3 snickerdoodles, and 2 vanilla cookies. She's going to pick a cookie at random, eat it, and then pick another cookie at random. What is the probability that she will pick a vanilla cookie first, then a snickerdoodle second? Well, the first one's easy. There's 10 total cookies, so her probability of selecting a vanilla is 2 out of 10, since 2 of them are vanilla. But she's going to eat one of them. So whichever one she selects, and if she eats it, she's actually going to reduce the number of cookies, and it's going to change the proportion of the different cookies that are in there. So these are dependent events. That is, the probability of selecting a snickerdoodle second is going to depend on which cookie she selected in the first selection and which one she ate. So it's a disguised dependent question. Well, we now only have 9 cookies left. We still have 3 snickerdoodles because the first one she ate was a vanilla, and so it's 3 out of 9. We multiply those and we get 6 over 90, or 1/15. Let's go to 3D now. Joan has a strange computer keyboard. There are only 6 letters, A, E, L, M, N, P. Joan will type one of the letters at random, then type a second letter at random. She may type the same letter twice. Well, this suggests that we have an independent series of events, because whatever she picks the first time to type has no effect on the probability of picking a given letter the second time, since they're all going to still be available no matter what she selects the first time. So what is the probability that the first letter she will type will be a vowel and the second an M? So in the first situation, it has to be a vowel. In the second situation, it has to be an M. There are 2 vowels, A and E, so 2 of the 6 are vowels, and then 1 of the 6 is an M, and we multiply those probabilities out, and that's going to give us 2/36, or 1/18. All right, so that's independent versus dependent, very important concept. And now it's time, a short break. Let's take a look and see what Holly's up to. All right, why don't we move on to page 3 now? And we've been looking up until now at calculating the probability of multiple events happening. Let's take a look at a couple of issues that appear with single event problems, when only one selection is made, some tricky situations. First, we're going to look at what we'll call the OR problems. So the classical wording is, what is the probability of event A or event B occurring? Well, the short answer is you just simply add the individual probabilities. How to solve: if a problem asks for the probability of any of 2 or more events occurring, A, it says here, add up the probabilities of the individual events. But if any of the events can happen at the same time, you have to subtract the overlaps. Well, what do we mean by that? Let's take a look at an example. So 4A, a container contains 4 blocks. 2 of the blocks are cubes and 2 are spheres. So I'm going to quickly draw those in. By the way, how do you draw a block or a cube or a box? Draw 2 diagonally overlapping squares, or rectangles if you wish, and just connect the corners, and you've got quick, easy peasy boxes or cubes. And I'm just going to draw circles to represent spheres. We have 4 blocks. 2 of them are cubes, 2 of them are spheres. Now one cube is white and the other black, so I'll shade one of them in. One sphere is white and the other black, so I'll shade one of them in. Napoleon selects one of the 4 blocks at random. What is the probability the block will be a cube or be black? So again, it's an OR situation. Let's find the individual probabilities. 2 of the 4 blocks are cubes. 2 of the 4 blocks are black. But now, because we have an or situation, we have to make sure we don't have an overlap. What do I mean by an overlap? Are there any blocks that are both a cube and black? Well, yes, we have one black cube, and that we're going to subtract. And that's how easy it is. We have 3/4 then a probability of selecting a cube that is either black or a cube. All right, so let's have you try this out. This is an important topic, so we're going to have you do 4B, 4C, and 4D. Stop the video and come on back when you're done. All right, let's take a look at problem 4B to get us going here. There are 15 dogs in a kennel. We have 5 pugs, 6 terriers, and 4 boxers. Elizabeth will select one dog at random to take on a walk. What is the probability the dog will be a boxer or a pug? Well, there are 4 boxers, so the probability is 4/15 of selecting a boxer. We have 5 pugs, so we have a 5 out of 15 chance of selecting a pug. Now there are no overlaps. There are no dogs that are boxers and pugs. So no overlaps. And so we're going to subtract 0, and our final probability will be then 9/15 or 3/5. When there are no overlaps, the events or the outcomes are known as mutually exclusive. Mutually exclusive outcomes, there is no overlap. So that means you can skip the subtraction part. Skip the subtraction part. That's hard to say quickly 5 times. Going to 4C now. Smith holds 10 cards. 2 are blue, 2 are red, 2 are white, 2 are yellow, 2 are green. And one card of each color has a picture of a house on it, and the other card of each color has a car pictured on it. Smith will select a card at random. What is the probability the card will be house or yellow? Well, half of the cards have a picture of a house on them, so the probability of selecting a card with a house on it is 5/10. Now, 2 of the 10 are yellow, so we have a 2/10 chance of selecting a yellow card. But we do have one card that is both yellow and has a house pictured on it, so we have to subtract that one away. And when you add all of this together, we get 6/10, or again, 3/5. You'll keep getting the same answers here. Shows you my lack of imagination. 4D, today the probability of snow falling is 3/7. The probability of rain is 2/7, and the probability of hail is 1/7. These weather events are mutually exclusive. What is the probability that it will snow or hail? Well, mutually exclusive, you remember, when you see that, that means no overlap. Also, you'll notice that the probabilities don't add up to 1. Well, it doesn't matter. Since the events are mutually exclusive, it doesn't really matter what makes up the other 1/7 probability that's missing here from the problem. All right, mutually exclusive. So snow, probability is 3/7. Hail, probability is 1/7. And we just add those up and we get 4/7. And that is that. Okay, there are probability problems that involve playing cards. You're expected to be familiar with playing cards, or even if they explain them to you in a problem, well, you don't want to learn how a pack of playing cards works in the middle of the ACT. You're expected to know how a standard deck of playing cards looks. There are a total of 52 cards, and the cards come in 4 equal numbers of suits. 52 divided by 4 is 13, so you have 13 each of clubs, diamonds, hearts, and spades. Those are the 4 suits. The clubs and spades are black, the diamonds and hearts are all red. Now, sprinkled across each of the suits, there are 13 different card types. There's an ace card. There are individual cards of value from 2 to 10 each. We have jacks, queens, and kings. Those are worth 10 points each. Jacks, queens, and kings are called face cards because there is a face on them. Every different card type then appears 4 times, once in each suit. For example, there are 4 cards with a face value of 2. The 2 of aces, the 2 of clubs, the 2 of hearts, and the 2 of spades. Now, I do not actually own a pack of cards, but I have found a picture on the internet, so here's my phone. You will notice there are 4 cards in the pack on which a 7 is printed or have a face value of 7. There is 1 for each suit. The diamond looks like a diamond and the heart looks like a heart. Those are red. This thing here with the 3 leaves, that's a club. And then the spades is this other one here. And the clubs and the spades are black. There are 4 sevens, just like as there are 4 sixes, there are 4 kings and 4 queens, and so on and so forth. We're going to head over now to section 5 on page 4, restricted number of outcomes problems. These are problems in which the number of possible outcomes is reduced. What does that mean? Let's take a look at an example. 5a, what is the probability that a 6 is rolled with a fair die? Well, we know that's 1/6. A fair die is rolled, says 5b. Given that an odd number is rolled, what is the probability that a 3 will come out on top? All right, what does that mean? Normally, there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, or 6. Suppose that we take away the 2, the 4, and the 6 as possible outcomes. It has to be a 1, 3, or 5. We're limiting the number of possible outcomes. It's a given that 1, 3, or 5, an odd number, will be rolled. So we only have 3 possible outcomes to work with. Well, out of those 3, one of them is a 3 itself, and so the probability of rolling a 3 when you only have 3 options left out of the original 6 is 1 out of 3, of course. All right, let's see if you can apply that idea to 5C and 5D. Go ahead and stop the video. Let's take a look at 5C. Ulf has 8 favorite years of music. If Ulf selects a record from one of his favorite years at random, what is the probability that he will pick 1996, given that he only selects from a year in the 1990s? So even though there's a total number of 8 years in which Ulf likes music, he's limiting his selection to the 4 years from the 1990s. So we're reducing our potential denominator from 8 outcomes to only 4, of which 1 is 1996. And so we have 1/4 of a chance of picking a record from that year. In 5D, we have a high school, and it says here that we're only going to select from amongst the seniors only. We're going to select a student at random from the seniors only. So instead of taking all of the students as our denominator, as our potential outcomes, we're only selecting from the seniors. So we only have 30 potential outcomes here, 30 potential results. And what is the probability that the selected student will be a girl? Well, there's 20 girls out of the 30, so 20 over 30, or 2/3. Let's move to section 6, conditional probability. Conditional probability is very, very easy. This is really just a matter of common sense. We're applying the ideas of independent and dependent results into a specific type of problem in which you are asked to find the probability of an event occurring given a specific outcome in a previous selection or selections or outcome. Example 6a, if a die is rolled 10 times and a 4 comes out on top on all 10 of those rolls, what is the probability that a 4 will come out on top on the 11th roll? So these are independent events. Each roll of a die has no effect on subsequent rolls. So no matter how many times you roll it, the probability that a 4 will come out on top, and in this case here on the 11th roll, is still just 1 out of 6. All right, again, very straightforward stuff here. Stop the video and let's have you try 6B and 6C. In 6B, Genevieve, it says, selects a card at random from a standard deck of cards, pulling out the Queen of the Hearts. She does not replace it. What is the probability of her selecting an ace at random from the remaining cards? Well, these are dependent events because depending on what card she pulled out, that would have an effect on the probability of pulling out an ace in the subsequent one. And because now we only have 51 cards left and 4 aces remaining in the deck, we have a 4 over 51 chance. Similarly, now, Genevieve again selects a card. Again, she pulls out the Queen of Hearts, but this time she replaces it. What is the probability of her selecting a queen at random from the remaining cards? Well, now they're independent because no matter what she pulls out, she puts it back into the deck. So it has no effect on the selection that we're going to do now in the second place. So selecting a queen at random from the remaining cards, well, there's 52 cards back again total, of which 4 are queens, so 4 out of 52, or 1 out of 13. That concludes the lessons part of this video. There are some extra practice problems in section 7. So if you want to go ahead and do those, do those. Stop the video and just go ahead and do 7A, 7B, 7C, 7D. And when we return, we'll go over them. And then after that, we'll take a look at how to reduce fractions on your calculator. So stop the video and go ahead and do the section 7 problems. In 7A, we have a card that will be picked at random from a standard deck of cards. What is the probability that the card will be queen or red? So an OR problem, so we're going to add the individual probabilities. We have a 4 out of 52 chance of picking a queen. Now the red cards, that's half the deck. So we have a 26 out of 52 chance of selecting a red card. And how many overlaps are there? That is to say, how many cards are there that are red with a queen on them? Well, that's going to be the queen of diamonds and the queen of hearts, 2 out of the 52. And so we're going to add the individual probabilities and subtract the overlap. And that's going to give us 28 over 52, or simplified 7 over 13. 7B, the Jonestown baseball team has a 0.4 chance of winning Saturday, a 0.3 chance of winning on Sunday. What is the probability that the team will lose on Saturday and win on Sunday? And these are independent events. So we're just going to multiply the respective probabilities. Now for Saturday, the question is requiring us that they lose on Saturday. So if they have a 0.4 chance of winning, they have a 0.6 chance of losing, because the either winning or losing has to add up to 1. And Sunday, they have a 0.3 chance of winning, and we're required in the problem to have them win on Sunday. So 0.3 on Sunday, we're going to multiply those. 0.18 is our final answer. That's our probability. I suppose the question might allow for a draw, but we'll just assume for purposes of this question that it has to be either win or lose. Going to 7C now, a card is to be selected from a standard deck of cards. We're only going to select from the spades. There are 13 spades. What is the probability that the selected card will have a face value of 3, 4, or 5? Well, we're going to add the individual probabilities. We're only selecting from the spade card, so not all 52 cards, but only of the 13. We're reducing our potential denominator. What is the probability that it will have a face value of 3, 4, or 5? So it's a 1/13th chance that it'll be any of those. Since there are no cards that have values of 3, 4, and 5, or any combination of those, they're mutually exclusive. We're not going to subtract anything, and our final answer is 3/13. Finally, 7D, Athena will select 2 cards at random without replacement. What will be the probability that the first card she selects is a face card and the second an ace? So there's 4 of each. So in her first selection, we're going to have a 12 out of 52 possibility of meeting the requirement of the problem to have a jack, queen, or king. Now, because it's without replacement, for the second selection, there's only going to be 51 cards left. There are 4 aces left. So the probability of the second event occurring is 4 out of 51. And we're going to multiply those out. And if I did this correctly, we get 48 out of 2652, which simplifies into 4 over 221. Stay tuned if you want to learn how to reduce fractions on your calculator. Otherwise, thank you for watching, and we'll see you next time. Let's take a quick look on how to reduce a fraction on your calculator. The secret formula is math, enter, enter. If you did not know this, if they did not teach this to you in school on the first day that you received this calculator, then your education has been sorely lacking. They have been negligent indeed. Let's do an example. Well, I'm just going to do 5 over 10, right? Just enter that on the calculator. So 5 divided by 10, and you got to enter it. So you got to end up with a decimal, right? So let it go to a decimal. And then I'm just going to do math, enter, enter, and there it is, 1/2. So you can reduce any fraction on your calculator by getting it into decimal form, and then your math, enter, enter is your magic formula there. And anytime you do any math at all on your calculator and you get a decimal answer, you can always convert it into a fraction by doing that. So let's say, for example, I'll just do 4 plus 6, um, enter that, and then times 8, enter that, and then divided by 125 and enter that. And now I just want to turn that back into a fraction. So hit math, enter, enter, and there's my result, 16/25 in its smallest form, most reduced form. And that is that. So thank you all, and we'll see you in the next video.